All right, are we ready for section 2.3, graphs in science? All right, it's been a long day and all you can think about is food. You toss down your gym bag and head into the kitchen. Now for some pasta. You set a pot of water on the stove and turn on the heat and wait eagerly for the water to boil. Several minutes later, you are still waiting for the first sign of bubbles. Could the saying, "a watched pot never boils," really be true? Or is it the water taking longer to boil today because you filled the pot more than usual? Is the volume of water related to the boiling point? You could do an experiment and collect some data to find out. The importance of graphs. In Chapter 1, you learned why it is important to organize the data you collect in an experiment. Creating a data table is one way to organize experimental data. Another way is to show data is in the form of a graph. You can think of a graph as a picture of your data. Have you ever heard the saying, "a picture is worth 1,000 words"? This is exactly why graphs are such a useful tool. Because of the visual nature, graphs can reveal patterns or trends that words and data tables cannot. The three types of graphs that scientists commonly use are bar graphs, circle graphs, and line graphs. You can learn about these graphs in the Skills Handbook. This section focuses specifically on line graphs, how to create them, and how to interpret the patterns they reveal. Okay. Why are graphs useful? Suppose you set up the experiment in figure 15. You record the data table, the time it takes each pot of water to boil. From your data table, you can tell that as the volume of water increases, the boiling time seems to increase as well. But a line graph could reveal more clearly how these two variables are related. Line graphs are used to display data to show how one variable, the responding variable, changes in response to another variable, the manipulated variable. In the water boiling experiment, the responding variable is the time it takes for the water to boil. The manipulated variable is the volume of water in the pot. So here's our data. 500 milliliters takes 7.8 minutes. 1,000 equals 16.6 minutes. 1,500 milliliters equals 26 minutes, and 2,000 milliliters equals 33.7 minutes. Okay, we're going to use this. Okay, plot a line graph. When should you plot a line graph? The answer is when your manipulated variable is continuous. That is, when there are points between ones that you tested. In the water boiling experiment, volumes are 501 milliliters, 502 milliliters, and so on. Exists between 500 milliliters and 2,000 milliliters. Time and mass are continuous variables. To plot a line graph on your data, follow these steps. Okay, draw the axes. The horizontal axis or the x-axis is a graph that runs left to right, horizontal, right? The vertical or y-axis is the graph that runs up or down. So this is vertical. This is your y-axis. Label the axes. Label the axis with the name of the horizontal axis or the x-axis is the manipulated variable. This is very important in science. You must identify your manipulated variable and put that on your horizontal axis. The vertical axis is the name of the responding variable. Be sure to include the units of each axis. So again, horizontal is manipulated variable. The vertical axis is the responding variable. It's important. You do have to label your graphs this way in science. Okay, create a scale. On each axis, create a scale by marking off equally spaced intervals that cover the range of values that you will show. Both scales should begin at 0 when possible. The point where the two axes cross is called the origin of the graph. On the graph, the origin is the coordinate 0, 0, which represents 0 milliliters and 0 minutes. A coordinate is a pair of numbers used to determine the position of a point on a graph. Plot the data. Plot a point for each piece of data. The dotted line shows how to plot your first piece of data. So it's 500, 7.8. Following an imaginary vertical line extended up from the horizontal axis at the 500 milliliter mark. Then follow an imaginary horizontal line extending across the vertical axis at 7.8 minutes mark. Plot a point where these two lines cross or intersect. The point shown at this location of the intersection is called the data point. Then the last step is to draw a line of best fit. A line of best fit is a smooth line that reflects the general pattern of a graph. Though your first instinct may be simply connect the dots, that's not the correct approach to drawing a line graph. Rather, you should first stop and look at the point you plotted to identify a general trend in the data. Then draw a smooth line between the points to reflect the general pattern. Notice that the resulting line of best fit for this graph is a straight line. A line graph in which the data points yield a straight line is called a linear graph. 6. Add titles to identify the variables or relationship between the graph. Okay, you can see in this one with the horizontal and vertical axis. 2, we labeled the axes, okay, with a manipulated and responding variable. We created a scale here. Then we plot the data. Okay, draw a line of best fit and then add a title. All right, why do we draw a line of best fit? You may be wondering why you cannot simply connect all your data points with a line to create a line graph. To understand why this is the case, consider the following situations. Suppose your friend performs the same water boiling experiment as you did and plots the graph shown in figure 17. Notice that your friend's graph shows the same general trend as yours, points going upward from left to right. However, if your friend simply connects the dots, the line would be in a zigzag pattern rather than a straight line. Why don't your friend's data points fall perfectly along a straight line? It's because whenever data is collected, small measurement errors and inaccuracies can be introduced. By simply connecting the dots, you would place too much importance on individual data points in determining the overall shape of the line. A line of best fit emphasizes the overall trend shown by all the data that is taken as a whole. Slope. Okay, when a line graph is linear, you can determine a value called a slope. One way to determine slope is the steepness of the graph line. The slope of a graph line tells you how much y changes for every change in x. Thus, another definition of slope is the ratio of the vertical change, the rise, to the horizontal change, the run. Slope is calculated using this formula. Slope equals rise over run. So you're going to find two data points and you're going to find the difference in the y and the difference in the x, and then you're going to divide the two. So to calculate slope, pick any 2 points on the line and write down the coordinates. In figure 18, suppose you choose the points 20, 10, and 50, 25. So what you're going to do is you're going to take the y-axis and you're going to take 25 minus 10, gives you 15 kilometers. On the run side, you take 15 minus 20, which gives you 30 minutes. So your slope is going to be 0.5 of a kilometer per minute. In this case, figure 18, the slope represents the distance the car travels per unit of time or speed. A slope of 0.5 tells you that the car speed is 0.5 of a kilometer per minute. Okay. Math analyzing data. This is going to be part of your homework tonight. Okay, using graphs to identify trends. Your data won't always give you a graph with a straight line. A line graph in which the data points do not fall along a straight line is called a nonlinear graph. Whether a graph is linear or nonlinear, the information it contains is very useful. The line graphs are powerful tools in science because they allow you to identify trends, making predictions. Linear trends. When a graph is linear, you can easily see how two variables are related. For instance, graph A in figure 19 shows that the farther one student stands from a basketball hoop, the fewer basketballs she can make. You can use the graph to make predictions. For example, how many baskets can she make at a distance of 5 meters? If you extend the graph line, you can see what your predictions would be. So, this is, okay, let's see, where is that at? Okay, it's up here, okay? So at 5, you would extend the line down and say, oh, she can make 1 basket, okay? That's how you would use that graph. Nonlinear trends. There are several kinds of nonlinear graphs. In some nonlinear graphs, the data points may fall along a curve. A curve may be shallow or it may be steep, as in graph B. Other nonlinear graphs show different trends. A graph might rise and then level off, as in graph C, or a graph may show repeating patterns in graph D. Because each of these graphs reveal a trend in the data, they are useful in understanding how the variables are related. Okay? So a nonlinear trend here. On a bike ride, the distance you bike increases with time. If you stop to rest, the distance remains the same and the graph levels off. And D, nonlinear trends. In many places, rainfall varies with the season. This graph shows a repeating circular pattern. So it rains a lot in January and then starts decreasing where you don't really have much rain in June. And again, you see by January, it's increased a lot. Again, the next year by June, it has decreased. So you can see that the rainy months are January and not so much rain falls in June. Okay, no trend. In other nonlinear graphs, the data points may be scattered about in no recognizable pattern, as in graph E. Would you be surprised to learn that even such graphs are useful? When there are no identical trends in a graph, it is most likely means that there is no relationship between two variables. So here in E, the amount of television shows children watch and their age are not related. The data points are scattered and the graph shows no recognizable pattern. Okay, homework for today is you were supposed to do the math analyzing data that we saw earlier and section 3 assessment. All right, I will see you all tomorrow. Bye.